Uh, we will discuss in this presentation for the stability of multidimensional systems. Let's say that you have a two-dimensional digital filter that is described by this transfer function. From engineering point of view, it is important for us to know if this transfer function describes a stable system or an unstable system. We know from one-dimensional case that the stability depends only on the denominator. But in two-dimensional digital filters, or in general in multidimensional filters, stability has to do with both numerator and denominator. Okay? Without loss of generality, we can assume that always the polynomial of denominator has as coefficient of the constant 1, because if it is not 1 and it is something else, you can divide numerator and denominator with this constant. So under these consumptions, we will try to find criteria and theorems for stability. The first theorem that we learn is that a system is BIBO input, BIBO stable, that means bounded input, bounded output stability, if we have this condition. This condition means that P is an integer value, and this condition is a necessary condition. If your system is stable, then for every P integer, and this is that means that this double sum is bounded. This is a necessary condition, but only if P is equal to 1, then this condition is necessary and sufficient. If P is equal to 2 or 3, etc., this condition is only necessary for stability. That means that if your system, your two-dimensional system is stable, then you have this condition is true for every P integer, but only if P is equal to 1, this condition is necessary and sufficient. And this theorem can be proved. But this theorem practically is not very useful, because we must have something more practical. So another more practical theorem is the theorem of Shanks. What does the theorem of Shanks say? The theorem of Shanks says that if you have a two-dimensional digital filter represented by the transfer function of this equation, then this system is stable in BIBO, bounded input, bounded output sense, if the polynomial of denominator, this is the polynomial of denominator, does not have points inside the unit by disk that vanish the denominator. That means you don't have points z1, z2 in -1. You don't have such points that this polynomial is 0. And you don't have non-essential singularities of the second kind between numerator and denominator. That means you don't have common factors between these polynomials, n and d. This is the so-called theorem of Shanks. This theorem is important, because if you have, in the case that you have non-essential singularities of the second kind in two polynomials, the theorem of Shanks cannot conclude. So, for example, you have here two different transfer functions. For both of them, the denominator does not have points z1 and z2 inside the unit by disk that makes it 0. But you have also for z1 equal to 1 and z2 equal to 1, this is 0, and this is 0, and this is 0, and this is 0. So this theorem cannot conclude. We don't know. If we make analysis, of course, further analysis, we can prove that the first is stable while the second is unstable. So we need more practical theorems. If your transfer function has non-essential singularities of the first kind, of Bibo stability, then that means that your system does not, the denominator does not have zeros, but the inverse is not true. Another theorem is this: if the denominator does not vanishes inside the unit by disk, then you have this condition. About theorem 5.5, if your system is Bibo stable, then you have this. What does it mean? This means this. If your system is stable, then this is true for P equal to 2, but the inverse is not true, because as I told you, only if P is equal to 1, this condition is necessary and sufficient. Let's continue with the theorem of Hwang. The theorem of Hwang says this: a two-dimensional digital filter is Bibo stable if and only if you have these two conditions. This theorem is much better for us, and we can implement it with better than the previous one, because the first condition is one-dimensional condition. This is much easier to be checked. Why? This is much easier to be checked because this is a polynomial of only one variable, z1, and this is a one-dimensional condition. This is semi-two-dimensional conditions, because of course z1, z2 takes values in the unit by disk, in the unit disk of z2, but z1 takes values only in the border. So this theorem is an important simplification, and of course we can write this theorem in its dual form. The dual form of this theorem is d0 z2 minus 1 for z2 minus 1 smaller or equal to 1, and this different than 0 for z1 minus 1 smaller or equal to 1, and z2 minus 1 equal in absolute value equal to 1. The proof of this theorem is here. Theorem of Stringes. Stringes was professor in the Aristotle University of Thessaloniki, and this theorem made him famous. And now in bibliography, this theorem is called theorem de Carlo-Stringes because Carlo and Stringes discovered this theorem simultaneously and independently each other. A two-dimensional digital filter, theorem of Stringes, Michalis Stringes. A two-dimensional digital filter is Bibo stable if and only if. Stringes told this: you must put here a constant value instead of z1, here another constant value instead of z2, but what kind of constant value? Constant value must fulfill these inequalities, and then you check this one-dimensional condition, this one-dimensional condition, and this two-dimensional condition, special two-dimensional conditions, where z1 and z2 in absolute value is equal to 1. This is the theorem of Stringes. As corollary in the theorem of Stringes, you can have this, where alpha and beta are equal to 1. This is a special case of theorem of Stringes, and we can see it as corollary. De Carlo, Murray, and Sykes proposed this technique, this theorem for stability of two-dimensional system. And two-dimensional digital filter is bounded input, bounded output. What does it mean, bounded input, bounded output? Bounded input, bounded output, two-dimensional system or two-dimensional filter, maybe filter that process an image. Bounded input, bounded output means for every bounded input that you have in your system, the output is also bounded. Bounded means the signal must be in a zone like this, must be a bounded signal. So a two-dimensional digital filter is Bibo stable if and only if you have this. This is the formulation of De Carlo, Murray, and Sykes. D, always the D is the denominator, the polynomial in the denominator. We have this. Here we replace Z1 and Z2. This is not typing error. Instead of Z1 and Z2, we use the variable Z. And we must check this condition. This condition is one-dimensional condition. And also, we check this, but this condition is for absolute value Z1 and absolute value Z2 equal to 1. So here we don't go inside the unit disk, only on the border. And here we are in every point of the disk, but the variable is 1. These theorems are good, but it is not easy to be implemented. And why we have to check the stability of a filter? Because we must design a filter, and if we design a filter, from engineering point of view, we must be sure that this filter is stable. Stable means for every bounded input, the output must be also bounded. If your filter is not stable, then from engineering point of view is useless. So we must have practical tests to examine stability. And why we must have practical tests? Because when we design a filter, our system usually is reduced to an optimization problem. And if you have to solve an optimization problem, you must have some conditions. So in order to check a condition like this is practical impossible. But if you have to check conditions like this, then the conditions that we will show now, then these conditions can be constraints in an optimization problem, and you can solve this problem with optimization. So the problem, the design of two-dimensional filters, practically gives an optimization problem, and we have published some papers, and some of them in IEEE, that we can solve this optimization problem via neural networks or via genetic algorithms. The next theorem says that the zeros of polynomial Pz, designated as Z1, for I equal 1 to n, are located in the open unit disk if and only if we have this. This is not a theorem of two-dimensional systems. This is a theorem of one-dimensional system, but this is the necessary background, the necessary theorem that we use in order to prove a theorem for two-dimensional systems. This is theorem for one-dimensional polynomials. I omit some mathematical details, and finally we have this formulation. The zeros of polynomial Pz are located in the open unit disk if and only if the Shurikon matrix K in equation 5.12 is positive definite, where the construction of matrix K and the application of theorem 5.10 constitute the Shurikon 1D stability criterion. Matrix K can be checked for positive definites by diagonalizing it and checking its diagonal elements, by computing the determinants of its principal minors, by finding its eigenvalues. If the diagonal elements in A or the determinants in B or the eigenvalues in C are all positive, then K is positive definite. So the Jury-Marden and Shurikon stability criteria necessitate that polynomials in Z1 minus 1 or Z2 minus 1 be changed into polynomials in Z1s or Z2 by multiplying them by Z1 n1 and Z2 n2. What we say here is that we start with the theorem of stability of one-dimensional polynomials, and we can write the polynomial in two dimensions in an appropriate way, where you have, for example, a polynomial of Z1 and Z2. You can see it as polynomial of Z2 with coefficients that are polynomials of Z1, or polynomial of Z1 with coefficients that that are polynomials of Z2. If we take this in our account, then it is easy to find the Surcon Hermitian matrix. Here we can find the Surcon Hermitian matrix here, and we can have this theorem. The condition in equation 5.14 holds if and only if the Surcon matrix CZ1 in equation 5.15 is positive definite. Where is the Surcon matrix? The Surcon matrix is given by the equation 5.15. Further progress in this analysis can be made by noting the following results, which are due to Siljac. Matrix Z1 minus 1 is positive definite is positive definite for Z1 minus 1 absolute value is equal to 1 if and only if you have these two conditions. C1 is positive definite matrix, and F Z1 minus 1 is determinant. The determinant is positive for Z1 absolute value is equal to 1. By defining a polynomial GZ1 as this, the condition in equation 5.16b can be transformed into the simpler but equivalent conditions 5.18a and 5.18b. Evidently, the condition in equation 5.18b involves a polynomial in one variable and can therefore be easily checked by finding the roots of GZ1 using a reliable software package like MATLAB or by applying a recursive procedure described by Siljac. The preceding results can be summarized here. And here we have a numerical example because if you have a nice mathematical theorem, always you must apply it in some numerical examples and to see if your algorithm works in some numerical examples. So, for example, here we have a two-dimensional digital filter in this transfer function where D is equal this, and we must check this filter for stability. Okay, how we can proceed? The polynomial dz1 0 is this. This polynomial has two zeros, z1 minus 1 equal to 2, and hence the condition in equation 5.7a is satisfied. Polynomial says z2 given by equation 5.13 can be written as follows. Since the highest power of z2 is 1, the Surcon matrix for z1 minus 1 absolute value given by equation 5.15, where is the equation 5.15? 5.15 is how we create the Surcon matrix, Surcon Hermitian matrix. 5.15 is a 1-1 matrix, 1 by 1 matrix, and can be expressed as follows. Hence, we have these conditions. C1 is equal 0.0254, and the condition in equation 5.16a is satisfied. From equations 5.16b and 5.17, the polynomial gz1 can be obtained as follows, and we can find g1 is positive. That is the condition, both of the condition of equation 5.18a is satisfied, and finally the zeros of gz1 can be obtained as follows. Therefore, our conclusion is that the filter is stable. I will omit these things. And here we have another methodology. Other methodology demands other methodologies when two polynomials have no common zeros. Two polynomials, this is a result from elementary algebra, but it is very useful if we want to create an algorithm for the stability of two-dimensional systems. Pz and Qz are two polynomials in one variable z and do not have common factor, do not have common zero if and only if this determinant is not zero. And what is this determinant? This determinant is called resultant the matrix R, the determinant of the matrix R is called resultant matrix. And the resultant matrix can be formulated as follows. You have the coefficients of the polynomials, P0, P1, etc., Pn, P0, P1, Pn, and this, and you check if the determinant, if this matrix is invertible. You must not have this determinant 0. Okay. This is very useful. We will extend this result in two-dimensional case, but in two-dimensional case, now these coefficients will be functions of Z1 or Z2. So, stability analysis in frequency domain has these steps. First step, we must write the polynomial D and these two polynomials. What are these two polynomials? One is the polynomial of numerator, the other is the polynomial of denominator. You must write as follows, where B and B bar are polynomials of Z1. Second step, we find the roots of 1D algebraic equation and represent them by this. If this is not equal to 1 for all I in the range this, then the condition in equation 5.19 holds. Otherwise, we go to step 3. If Z11 in minus 1 is equal to 1 for some I, then we substitute the root, this root, in D, and we find the roots of D bar. If one of the roots obtained is on the unit circle, then the condition in equation 5.19 is violated. We repeat this step for each root, Zij in minus 1, whose magnitude is 1. If no roots of D bar can be found inside the unit circle, then the condition of 5.19 holds. Example, you can study the stability of the same filter that we studied previously with the previous method. We had this system, and now, where is this? Wait a minute. We can apply the same system, the second method. This we can apply for the second system with n bar equal to 1. The second methodology for the same example. So if we apply this methodology and if we make all these necessary steps, we will find, of course, the same filter. The two different methodologies must find the same results. So if we follow this algorithm, we will find that this filter is also stable. Another approach for two-dimensional systems is the stability analysis in state-space domain. For the stability analysis in state-space domain, we try to find the state-space equation. And if we find the state-space equation, we can find that the denominator, the polynomial of the denominator, can be written as in equation 5.22a or 5.22b. Here we have this theorem. The transfer function of equation 5.20 represents a bounded input, bounded output stable digital filter. Your filter is stable in bounded input or bounded output sense if and only if one of the following conditions holds. And we have 4 conditions. If you discover the first 2, the third and the fourth condition are dual cases of 1 and D. First, all the eigenvalues of matrix A1. What is the matrix A1? The matrix A1 is the state space implementation of your model. Unfortunately, there are some mathematical details that you must know in order to understand what is matrix A1. And all the eigenvalues of matrices of this matrix for absolute value of Z1 equal to 1, must be located on the open unit disk. Similarly, we have the formulation of 2, 3, and 4. Here we have some numerical examples. For example, check the stability of these filters. Check the stability of these filters. Let's see the first. For the first, you find A1, A2, A3. And if you apply the previous things, you can find, for example, that this filter is unstable. And also the second filter is also unstable. Like the systems, the discrete systems in one case, you can have Lyapunov stability theory for two-dimensional case. Let's make a repetition for one-dimensional case. And one-dimensional filter can be described by these state space equations. And for this filter, you can have Lyapunov theorem that this filter is stable if and only if you can find for any positive definite matrix Q. What is positive definite matrix? You must recall some things from linear algebra. For any positive definite matrix Q, you have a unique positive definite matrix P that satisfies this equation. The proof is not difficult. Similarly, theorem exists for two-dimensional systems, and for two-dimensional systems we have the theorem of Lu and Li. A two-dimensional filter represented by the transfer function of equation 4.5 is Bibo stable if and only if matrix A1 has all its eigenvalues on the open unit disk. The Lyapunov equation, this Lyapunov equation 5.26, where Gz is given by the equation 5.27, has a unique positive definite Hermitian solution Pz. So, in a few words, the two-dimensional Lyapunov stability theorem is, of course, generalization of one-dimensional Lyapunov theorem, like this, but here the matrices do not contain numbers, but contain polynomials of one variable. After the theorem of Lu and Li, we have the theorem of Elagizi and Fami. The two-dimensional digital filter represented by the transfer function of 5.20 is Bibo stable if there exists a block diagonal positive definite matrix where W1 and W2 are positive definite matrices of dimensions n and m respectively, such that the matrix Q given by this equation is positive definite. The proof is here, and some results are here. Very important is to have tests for low-order filters to check the stability for low-order filters. Why this is very important? Because when you want to design a filter, a two-dimensional filter, for example, you consider that this two-dimensional filter, you solve an optimization problem and you approximate the ideal two-dimensional filter with a product of one-dimensional filters. For the product of one-dimensional filters, you have a product in the denominator where all the factors are polynomials of small dimension. Why you have polynomials of small dimensions? Because you have simple stability conditions. And you have simple stability conditions. For example, if you have a polynomial like this, then necessary and sufficient condition for stability is this. I repeat. Let's say that you have this two-dimensional system. Actually, you have a polynomial. You have a two-dimensional system for which the characteristic polynomial is this. So this is stable if and only if you have this. This is stable. This is the dual case if and only if you have this. Okay. Let's go in something more complicated. So here you have 1 plus this term, and the condition is this. Here you have 1 plus this term, and the condition is this. In case that you have these two terms, look, only this, you have added only one term, then you have these conditions, this or this. So only with a small modification you see how complicated are now your conditions for stability. And what about if you have this? If you have this, then the situation, you will have this, and they will give you the 5.38. And what about if you have this with n1 and n2 equal to 2? Unfortunately, in this case, you must check all these things. So even in this case, to design a two-dimensional filter with factors in the denominators of second-order polynomials, the situation is very, very complicated. So until now, we design a complicated two-dimensional filters where the transfer function has as denominator products of factors of first degree. So in the denominator you can have, in the most complicated case, you must have factors like this, not factors like this with n1 and n2 equal to 2, because the optimization problem is extremely difficult and complicated. Now, our research includes design of two-dimensional filters with genetic algorithms, neural networks, and other bio-inspired optimization algorithms. This was the end of my presentation.